Welcome to the next video. In this lecture video, we will be discussing the using of different droplet sizes, okay, for the performance of DPM simulation, okay. Now before that, as you have seen in the injection, I have selected the particle type as inert but not droplet, okay. So you must be thinking that I'm referring to water droplet, but why have I selected inert, okay. So in order to show you the evidence for that, I'll just come to this ANSYS Fluent what do you call manual, I'm sorry. So we have this list of particle types. I will be attaching this link in the resources in the notepad, so that will be very helpful for you to just read if you're free. And all the different particle types are being listed over here, and you can see the inert particle because we are dealing with this thing as of now. The inert particle is a discrete phased element. It can be a particle, it can be a droplet, or it can be a bubble that obeys the force balance. So we have already seen the force balance equation and we were discussing this thing, right? And it is subjected to heating or cooling via law 1. You can just code this section. There are different laws of heating and cooling. We are not considering the laws of that particular what you call the laws over here. Okay, we are not considering this thing, so we can just ignore them as of now, okay. And that is what is the reason why I've selected the inert particle rather than selecting droplet, okay. So this is a kind of further simplification in the process. Now let me just again come back to this injection properties, okay. Now the material, you're very clear with it. We have defined the material with 1000 kg per meter cube density, okay. Now in the diameter distribution, there is an option called as Rosin-Rammler. Now the pronunciation depends on the person's name, okay. I'm just pronouncing it as Rosin-Rammler. Maybe it can be correct or it may be incorrect, but the point is we have to understand what is that, okay. So let me just turn this on, and I'll just come back to our guide over here, and I'll just quickly go to the back, and yeah, using the Rosin-Rammler, because it is really important for one to regularly use the ANSYS manual, okay, because there are thousands of options which are present in ANSYS Fluent, right? For each model you'll be having different options. Again, for different options you'll be having different options further divided. So you cannot just play randomly with our own knowledge. We cannot do that thing. It is generally desired for individual to refer the manual before using any option or before dealing with any option, because we need to understand what is that, at least a simple definition of that function. And probably if you're having some interest in coding, or if you're someone from coding background as well, you know that the coders, the people who code, actually they are like, they'll be having numerous tabs open with different manuals, like Python manual. They'll be having Stack Overflow and different websites which help them with different people who support them for coding, right? As well as manuals, there'll be different manuals of Python, Java, etc. They'll be just looking at that, because nobody will remember the functions of each the definitions of each function, okay. You just have to refer the manual and get back to it, because if you are a person who is having an expertise in combustion, and for the first time if you're dealing with DPM model, then you cannot work. You just have to understand first the background, then you can just choose the options depending on your cases, right? That is the reason I'm referring the manual. Don't think that the instructor doesn't have knowledge and he's just referring the manual and explaining you, but I'm just trying to uh, teach you in a proper way so that you can just understand by keeping ANSYS as a reference, okay. I'm not here to say my own philosophies over here. I have to teach you what is existing thing in a better way, right? Now coming back to this Rosin-Rammler diameter distribution method, in the existing uniform method, what have we done? We have selected this diameter to be uniform, but when we are selecting the Rosin-Rammler method, the diameter will not be uniform. That means the diameter of the particle or the droplet which is entering into the domain will not be uniform. It will be varying. That is what is the Rosin-Rammler diameter distribution, okay. So for liquid sprays, a convenient representation of droplet size distribution is Rosin-Rammler expression. The complete range of sizes is divided into an adequate number of discrete intervals, each represented by a mean diameter for which trajectory calculations are performed. Okay, now in the previous case we have assumed that the diameter is uniform for the complete particle, all the particles that are imported or injected. But now we will be having different diameter particles, and for different diameter particles we will not be deciding the particle sizes. Like for example, we cannot decide, hey, you have to be so and so diameter and you have to be so and so diameter. That is impossible for us, because if our mesh is more denser, you'll be having more number of droplets entering into the domain, and it is impossible for a user to define the diameter of each and every droplet. So we have this mathematical calculation based on Rosin-Rammler distribution method. So in this method there are three requirements for us. We need to enter the minimum diameter of the desired particle. Okay, for example, these are the 66 particles which we are entering, which we are injecting. Okay, and I must decide that the minimum diameter should be some value for that 66 diameter. Okay, and the diameter should not cross a maximum diameter. Okay, so I need to enter a maximum diameter value, and when I'm taking the mean diameter of all the particles, the mean diameter should be having some specific value. So these three conditions we must define, and based on that the calculation will be done, and that will be automatically done by the software in the background. So we need not do anything, we need not worry about dividing them, we will be just entering the minimum diameter. So this is the smallest diameter to be considered in the size distribution, this is the largest diameter. So if we have a set of 66 particles, and if we are checking up the diameters of all of them, the minimum diameter will be having some value. Okay, and it will not be below this. Similarly, the maximum diameter will be some value, and it will not be more than that. Any other diameter will not be more than this maximum diameter, right? And if you're taking the mean diameters, you'll be having a specific value. So all these things should be sent by the user. Okay, the software cannot interpret. Depending on your case, you have to deal, right? Now as an assumption or as an sample simulation, I'm just considering these values. Okay, the minimum value will be 1